My name is Lee Chinitz. I'm the CTO at octoScope, and welcome to the first of our tutorials in 2021. Today, our tutorial is going to be on a feature of Wi-Fi 6 known as target wait time. This is a feature that we've been getting a lot of questions about, and we're pretty excited actually to be able to show what we've been able to put together from a testing perspective. So today on the tutorial, you've got me. Again, I'm Lee Chinitz. I'm the CTO at octoScope, and I've done several of these tutorials with my colleagues. So those of you who are not completely new to this will have seen me before. And together with me today is Jim Blout. This is his first time, and he's going to do all of the interesting and fun parts of this tutorial when we actually get to see TWT at work. Jim's a senior systems engineer. He's been doing wireless testing for a lot of years, as you can see, and he has really done an amazing job at visualizing what's going on with TWT. So that being said, let me give you a quick sketch of what we plan to go through today in the next hour. Again, we're going to talk TWT. It's target wait time. It is, among other things, a power save mechanism for Wi-Fi. So we're going to talk about TWT and Wi-Fi in general as how it relates to the Internet of Things, or the IoT. We're going to talk a little bit about how Wi-Fi has gone from possibly a position of some weakness from an IoT perspective to a position of strength in terms of the IoT. Then I'm going to talk specifically, give you a little bit of a history, just a quick walkthrough of power saving modes in Wi-Fi, what they do, what they were intended for, roughly how they worked. Then we'll talk about TWT in a lot more detail. And finally, we're going to move on to the demo. And we're going to leave plenty of room for the demo. I think it is really the reason most of you are probably here is to actually see if we can actually visualize TWT. The last item I have on this agenda is Q&A. Feel free to ask questions as we go along. All right, so let's talk a little bit about Wi-Fi 6. What's Wi-Fi 6 all about? We've actually done a number of tutorials on Wi-Fi 6 already. And one of the most important things to recognize about Wi-Fi 6 and how it's different from all the previous generations of Wi-Fi is that it's not an amendment to the specification focused on throughput, which typically they were before that, high throughput and very high throughput. Even now, extremely high throughput. It's always a throughput focus. But Wi-Fi 6 is not that. It's an efficiency focus. It's known as HE, or high efficiency. And one of the applications for this, among others, and it's not the only one, but the one we want to focus on today, is IoT. Support for IoT. So question is, what did Wi-Fi 6 add to Wi-Fi to make it more appropriate for the IoT? Well, there's at least two things. One is OFDMA, and at a high level, what OFDMA did was to allow Wi-Fi to be a lot more spectrally efficient when it is being used by low bandwidth devices. And then there's TWT, really the focus of the tutorial today. And what that does is it allows Wi-Fi devices to be a lot more efficient with their battery usage, and to allow those devices to last much longer. We'll talk about how as we go along. So I'm going to do a very, very quick touch here on OFDMA, and then we're not going to talk about that anymore today. Part of the reason for that is that we've done at least one major tutorial on OFDMA, and I think probably a few others where it was brought up. So anybody who didn't see those and is interested in a lot more depth, please take a look at the tutorials that we've posted already. But just real quickly, why is OFDMA something that's relevant to IoT? The answer is that it allows Wi-Fi users to use far less bandwidth than otherwise would have been possible. So before Wi-Fi 6, what we were always dealing with was what's represented by this little colored block here on the left-hand side. And in this colored block, on the horizontal axis, we have time. And on the vertical axis, we essentially have frequency. And what you can see is that at any given time, all of the channels, all of the entire channel would be allocated to a single user. So you can see first user 1, then user 2, user 3, etc. What that meant is that, the minimum amount of spectrum that a user could possibly get in Wi-Fi was one channel. So let's say one 20 megahertz channel. And, if you look at the data rates that, let's say 11AX is offering, even in a 20 megahertz channel, we're talking about, like 100 megahertz, 100 megabits per second or more. So, it's quite giving you quite a large amount of bandwidth, even if you're a small IoT device and you don't need it. There was kind of no way around that. But Wi-Fi 6 addresses that. So in Wi-Fi 6, we're talking about this little colored block here on the right. And what we have is, again, the same axes. But if you look now in any given time, you can see that we're able to allocate spectrum to more than one user simultaneously. So in the first time chunk, for example, we've allocated half of the band to user 2 and the other half to user 1. And then in the third time chunk, we've allocated a quarter of the band to users, looks like 4, I don't know, maybe 6, 2, and 1, something like that. So you can allocate much smaller frequency allocations to a given user in a given time, meaning that the entire network can be much more spectrally efficient for low bandwidth users. So just as a rough idea of understanding how much more efficient it can be, one of those 20 megahertz channels we talked about before, where previously you had to get the whole thing, they can be broken up into, about 1/10 that size. So instead of a 20 megahertz channel, you're talking about more like a 2 megahertz channel or so. It's really 1/9, but about that order. Let's see, we have a question. Will TWT and Wi-Fi 6 be able to be as low power as Bluetooth low energy for IoT and battery life? It's a good question. We're not going to get into comparisons with other technologies here today, mostly because I actually don't know the answer. I mean, I suppose if I knew it, I would say it. I can only imagine that there are people doing those experiments to find out. But what we want to do actually is just explain what Wi-Fi has done to try and be more spectrally and power efficient. So why is it important then to have access to less spectrum and not so much at any given time? And the reason is, if we're looking at the IoT, we're talking about what's likely to be a lot of little battery-powered devices that really don't have a lot of data to send, right? They're sending, occasional bursts of sort of telemetry-like data, all of which will be aggregated somewhere and wonderful things will be done with it. But it's not a lot of data to be sent at any given time. So allocating a whole channel, even just a whole 20 megahertz channel to support that, would be very inefficient. So again, OFDMA is about efficiency, not about throughput. It's about high efficiency. And so, allocating, smaller chunks of spectrum is more efficient that way, especially allocating smaller chunks of spectrum to multiple users simultaneously is much more efficient. And while we're talking about these little battery-powered devices, you also begin to realize that, oh, okay, so this is a different model from what people tended to think of Wi-Fi being about, right? We're now talking about devices that will run on battery, and we're not just talking about, can I get that device to run so that I don't have to charge it at least, more than once a day, or maybe once every 2 or 3 days. We're talking about times like months or even years, the kinds of times that people tend to think about for something like a smoke alarm in their house, where the battery doesn't get changed for quite a long time. So the way to do that is to be much more efficient with your transmitting and receiving. You want devices to be sleeping most of the time, and also not necessarily transmitting with multiple transmitters and receivers. Even single stream kinds of applications on very narrow bandwidths is much more efficient from a battery point of view. So what can Wi-Fi do about that? We've already talked about OFDMA. Let's talk now about batteries and TWT. Wi-Fi certainly has a reputation for draining batteries. I think everybody who's in the Wi-Fi space knows that. It was much worse in the old days. And part of the reason for this is just because of how the technology was designed, right? It was not designed. It was designed as a wireless Ethernet standard, and the idea there was you'd be dealing with laptops, even desktops back in the day. So things that were, yeah, sure, they could be moved around. They were plugged in quite a bit. They had a lot of power, and unlike a technology like cellular technologies, which right out of the gate were designed for devices that you were going to be, carrying around with you. It wasn't so much designed for that. And so that's how it got its initial reputation. But over the years, it's actually gotten a lot better at handling those kinds of small battery-powered devices. The reason that this is all important in the context of IoT is that we just got a question about Bluetooth, right? Bluetooth Low Energy. And there's absolutely a lot of technologies that are going to be used to support the IoT, but I think there's just kind of no question that Wi-Fi is going to be an important one of those. And the reason for that is just that, Wi-Fi is already where those devices are going to be, in homes and enterprises, warehouses, hospitals, all kinds of places. You've already got Wi-Fi networks deployed there. Certainly, there can be other types of networks deployed, but there's going to be a major demand for the existing network to be able to support the devices in a good way. And this chart just kind of shows that. If you look out, at the later edge of this chart, say around 2025, even though you hear a lot of conversation about IoT and 5G, and various cellular standards, things like that. If you look at least according to this prediction, how many of the devices will be supported by those technologies, you can see it's quite small compared to the very large number of devices that are going to be supported by personal area networking standards and local area networking standards like Wi-Fi. So anyway, it's going to be critical, and it's important for Wi-Fi to be able to do it, which is part of the reason that Wi-Fi 6 contains some of the capabilities it contains. So if we go back into the past and think about Wi-Fi and how it evolved, like I said, as a kind of an Ethernet, wireless Ethernet standard, its initial mode was something like, it's just awake all the time, right? It's just there. The thing is plugged in, and you're just providing, wireless connectivity. So it's not really a power saving mode at all, but it's the far end of the scale. In the initial spec, there is what is known as legacy power safe mode. And in that mode, and I'll have a little picture of it later, but the basic idea is that the devices could go to sleep, but they'd wake up and look at beacons every now and then to see whether or not packets were being held for it. And the idea, beacons in the network, for anyone who's not, sort of aware of this, is these are packets that are sent out on a regular basis. They give information to the devices in the network about kind of what's going on and capabilities of other devices in the network, things like that. So they're sent out on a fairly regular basis, about every 100 milliseconds or so. So when you talk about a device waking up, every beacon or every couple of beacons, you're talking about a device waking up a few times every second. So sleeping is good, and only having to wake up a few times a second is good, and it's better than being awake all the time, but it's a far cry from what you need to be able to support something like the IoT lifetimes. After legacy power save, as Wi-Fi became more and more a tool for mobile devices, not even necessarily cell phones initially, but like Wi-Fi phones. Back in the day, there were technologies created like UAPSD, I think unscheduled automatic power save delivery, where what this was enabling the devices to do was to essentially communicate with the infrastructure and have it hold packets for it until it wanted to wake up again in some number of beacons. That was fine for light loads like voice, which is what it was designed for, and actually became the basis for a power save mode that was part of the Wi-Fi Alliance specification, known as WMM, or wireless multimedia. So again, all focused on things like voice support over Wi-Fi networks. And then if you look at the spec itself, you'll see a lot of other kind of evolutions of the whole power saving concept. And I'm not going to get into all these things, but there are a number of different things that the spec itself considers to be, power save mode. But for the reason I mentioned before, having to do with the beacons, this isn't really, none of them are really sufficient for what we're talking about if we're thinking about IoT-like battery lifetimes. So again, if you look back at legacy power save, I already mentioned how this worked. Essentially what would happen is a station device could go to sleep and wake up every beacon or few beacon periods and, send and receive data, and then go back to sleep, either, again, for 1 or 2 or 3 beacons. Again, good because you can see how much of this time is spent sleeping, but it's still waking up several times every second. Even UAPSD, again, designed for voice, had a fairly rapid wake up time. What it did was it allowed the devices to go back to sleep and to send traffic even within a beacon period. The reason for this is that, again, since it was designed really around voice, and packetized voice tends to use a 20 millisecond framing time, what you would get was the device going to sleep and then sending and receiving these 20 milliseconds of voice information and going back to sleep and waking back up again to do another 20 milliseconds of voice. So you could do that several times, even within a beacon. So again, now you're sort of cramming yet more sleep time within a beacon period, all of which is good, it's great, but again, it's all tied to beacons. And again, those beacons are arriving many times every second. So if you do want the devices to be able to support not just sort of cellular-like lifetimes, but smoke alarm-like lifetimes, then you have to move away from days of life to months of life for a battery. And so you needed a big shift away from beacon timing. And that's what target wake time is all about. So target wake time, very roughly, generally, is technology that allows the station and the infrastructure to communicate and determine when and how frequently the station device is going to wake up to send or receive data. So there's a negotiation between the two to create what are known as service periods. And these service periods have these two major benefits. One is this ability to sleep for a long time. It's what I've been kind of harping on this whole time. So that conserves battery. And the other, which is one I haven't really mentioned yet, so I'm mentioning it now for the first time, and then we'll describe it a little bit more, is the ability to reduce contention between the users by avoiding simultaneous transmit of those devices. And that makes the network more efficient because you have fewer collisions, and it makes the devices more battery efficient because they only have to send their packets once. Again, we'll talk about that. So really roughly, again, in a similar kind of picture from before, what target wake time can look like is this. You've got, an AP, the infrastructure on the top here. You can have users that will negotiate a sleep time that, is of some duration. Then they'll wake up and they'll go back to sleep. And you can have another user that may negotiate a sleep-awake service period that's dramatically different, maybe a much longer sleep time. And it could also be, we don't show it here, but we'll actually show it in the demo, a much different awake duration. So the whole thing is much more flexible now in TWT. So in a picture that looks, more like the one we talked about before, what we've got now are the station and the infrastructure essentially negotiating service periods. And once the service period has been negotiated, the station can just go to sleep and it only has to wake up again on its next service period. And that service period does not have to have anything to do with beacons. It can be very short and beacon-like, or it can be extremely long. We'll describe a little bit later how they're calculated, how the specification put some parameters in place that will let you create extremely long periods. And so, it'll look something like this. You'll have the infrastructure, the AP, and a station, which will negotiate a schedule. There'll be sleeping going on. There's a beacon happening, but nobody cares. And then there'll be a service period where the device will wake up, then it'll send and receive some data. It'll go back to sleep. It'll keep doing that over and over again. And as you can see, there's no beacon even going on in here. I mean, beacons are happening, but it's not relevant to the to TWT. So from a spec point of view, TWT has a whole bunch of attributes that are defined, or kind of mechanisms, and I'm just going to sketch them here. When we do the demo, you'll see some of this, but not all of it. TWT was defined both for individual stations and also for groups of stations. So individuals obviously just means that one device is scheduling a service period between itself and the infrastructure, whereas in a broadcast group, the idea would be that there would be a service period scheduled for a whole group of devices. So far, we are not seeing much in terms of group TWT out there in the market, but we do see individual TWT being supported, and that's what we'll talk about today. There are two kinds of scheduling. One is called implicit, one's called explicit. Implicit just means that after a service period, when the station is going to figure out when its next service period is, it just does that based on this pre-negotiated schedule that it has with the AP, and it doesn't have to actually talk to the AP about it. Explicit means that it actually communicates with the AP to determine when the next period is. So you can imagine how the implicit one is probably more battery efficient, because you've eliminated some communication with the AP that's not specifically related to data. On the other hand, to the extent that there can be some sort of miscommunication or something like that, you can see how explicit would be maybe more robust. So it's a trade-off between, being absolutely certain and also saving battery. And then the flows themselves have similar structure. There's what's called unannounced flows and announced flows. In the unannounced case, when the devices wake up, the infrastructure doesn't have to wait to communicate with the station, because there's already an arrangement between the two, and the infrastructure is aware of when the station should be awake and ready to receive packets. So they're just sent. Again, you can imagine how that might be subject to at least some problems every now and then. So there's an announced mode, which is probably more robust. The AP won't send anything until it hears from the station first. But again, that's going to be slightly less power efficient, because now you're using your transmitter on the station to announce itself rather than having anything to do specifically with data. So again, it's sort of a schedule, sort of a trade-off between robustness and power saving. So I had mentioned before, I kind of teased the idea that TWT isn't really just about sleeping. Sleeping is, I think, a big focus of it, but it's also about scheduling, and that maybe is a little bit less obvious. So let me describe that a little bit. From a scheduling point of view, why is scheduling important? First of all, let's talk about why scheduling is important for battery saving. It's important because the whole goal here is to avoid sending or receiving, that is using the transmitter or using the receiver at times other than when absolutely necessary to communicate the data that you have. So you want to avoid waking up too often, which we've been talking about, but you also actually want to avoid having your packets collide with other packets as much as you can, because when they collide, they have to be resent. Now, Wi-Fi knows how to do that. It's not like it's a problem, but from a battery point of view, it means that a packet that could have been sent once has now been sent twice. And so that is obviously less efficient, and as much as possible, you like to avoid it. And the reason TWT can help you do that is that since there's a negotiation between the infrastructure and the station about when these service periods occur, the AP can actually schedule different devices to have their service periods occur at different times, and essentially eliminate contention from the network, at least for those devices. So let me give you a quick visual on that. In a typical, what's known as distributed coordination function of Wi-Fi, things would look like this. You have, an infrastructure and a bunch of little stations, and they're all sending their packets. And occasionally, just statistically, two of them will send packets at the same time. They'll collide on the air. That collision will be detected. It's fine, and it will the system will recover. But those two devices have now had to stay awake longer and send their packets again. So again, you want to avoid that as much as you can. With TWT, since the AP and the station have actually prearranged a schedule, that schedule can be arranged so that the transmission and reception is actually happening at different service period times, actual different times over the air. And so you can essentially avoid collision. So that is a kind of a really powerful aspect of TWT, and it is also something that is more and more important as if you focus on IoT, where you're talking about a lot of devices. This statistical kind of collision is more likely to happen the more devices you have. Let's see, we have a question coming up. I assume one reason to schedule the TWT between the station and the AP is that the AP will store data to send to the station and wait until the TWT not store the data. Or is the only reason to avoid contention? No, it's both, right? you do want the AP to hang on to anything that you have until you wake up. That's absolutely true. And so that's kind of the power save part of it. But I'm just pointing out that there's another aspect to it, which is the scheduling part of it. Because in addition to saying, well, I'm only going to wake up occasionally, you essentially have the system has the ability to say, and by the way, I'm not going to have two devices wake up at the same time and send their packets at the same time, kind of by mistake, and collide, and then have to deal with that issue too. How accurate must the synchronization be between the AP and the station? That's a good question. I don't know how accurate it has to be. The way that the timing works, when Jim is doing the demo, he may want to talk to a little bit, but the way that the timing works is that the service periods are based on, I know I made a whole big point about how beacons weren't related here, but now I'm going to bring beacons back into this just temporarily. Those service periods, the first service period after the negotiation between an AP and a station is based on a timestamp in a beacon. So essentially the AP and the station negotiate some stuff and they're like, okay, now we're going to have this sleep awake period, and that starts at this point. And the point at which that starts is based on a timestamp that is sent by the beacon. So essentially the station is getting the TWT timing from the infrastructure, from the AP. So they kind of synchronize each other. And again, I'll let Jim jump in on that when he does the demo, but I think that is a reasonably accurate answer to that question. Questions over here. What happens when the AP sends unannounced buffered data, but the station is sleeping? That's a good question also that I don't have an immediate answer to. I'm not sure we've seen that. Jim may know. Let him jump in right now. Jim, do you know off the top of your head?
Well, they're still on a schedule, so the AP shouldn't be doing that. We'll get into seeing how these service periods work, and there's very specific times when they're allowed to transmit and when they would be holding the data. So unannounced.
I assume that there is some recovery mechanism in case it sends data and the station is somehow gotten off schedule. I don't know what it is off the top of my head, though, I will admit. All right, so what we're gonna very soon get to the demo part of this. So what we're gonna show you is how we can visualize TWT operation. We can essentially set up the sessions that I described. We can manipulate those parameters, the sleep awake parameters, and we can actually see the effect of TWT using different awake and sleep parameters in terms of the overall throughput on the link. And then if we zoom in on actual packet arrivals, you can actually see what's going on over the air. So you can see the difference between the wake and sleep times. Real quick, for anybody who's not familiar with octoScope, give you a very, very quick overview of our test bed. As I mentioned, we've done now several of these tutorials, and what we've tried to do in general is to use this particular standardized configuration that we have, what we call a stack max, to do all the tests, to essentially show people how flexible this test bed is. It can do many, many different tests, and it is being used to do this TWT test. I'm going to show you, or actually Jim will show you the logical diagram. So physically it looks like this. It's roughly the size of a tall refrigerator. It's on wheels. It's not that big, but compared to a lot of chambers, but it is, it's about that size. It's made up of 5 separate chambers. You can see them here with the doors open on the left-hand side, closed on the right-hand side, and then a few other key elements that you'll need to know about when you see the logical diagram of how the test was done. We have RF cables that we use to transport the RF energy from chamber to chamber. They look like this in the picture. In real life, in the logical diagram, they look like these blue lines. Each one of these lines, these blue lines, for example, represents 4 RF cables. You'll see antennas. The antennas are obviously used to connect the devices under test. with other devices in the testbed. The key part of our testbeds is that they're over-the-air testbeds. So the device under test is almost always using an over-the-air connection, talking to some of these test antennas. And so when you look at the logical diagram, you see these little arrows. That's what that represents. As the RF energy is moved back and forth between the chambers, it goes through programmable attenuators, and they look like this thing on the right, but they look like this blue box with the arrow through it on the left. And then finally, in the testbed are our Wi-Fi test instruments that we call PALs. The PALs come in multiple types and configurations. We'll be using 2 of them today, and there are more than that. Some of them are built directly into the testbed. Others are able to be used in the testbed, but also able to be used out of the testbed, many different varieties. And I won't go into it in great detail, except to say that today, we'll be using some of these PAL instruments that we call stay PALs. You'll hear Jim, I think, talk about these stay PALs. And a stay PAL is a PAL that is very specifically designed to be a station device or sniffer. And we will be using one stay PAL that is a Windows operating system and one that's a Linux operating system. And Jim will go through that. I see a question. Understand the idea of the timestamp gets to stay synchronized. Yet both devices need clocks with a certain accuracy such that the AP is ready for exactly when the stay wakes up, since the clocks will drift. Low accuracy to avoid contention, the AP must schedule a wide time window. Doesn't actually. Okay, so I think Hal is making an interesting comment about drift. I don't know. We can take it offline, but yes, I don't know about drift. So yes, they synchronize each other when they start. But I guess if the period were very long, you would need to understand, the drift part of it, and that may be discussed somewhere in the spec. I'm not sure. I see one other question. Oh, so the question: do laptops connected to power outlets still negotiate TWT sleep periods, or do they only do that when they're running on battery power? So TWT is negotiated by the station. So I think it's actually, a choice. And my guess is that somebody manufacturing one of those could make that decision to, invoke it or not invoke it based on, the status of the battery or, the status of the AC adapter. That's my guess. I don't really know, but let me hand this off to Jim right now so that you can all see, TWT working, get a better feel for some of the things we've been talking about, and we'll continue some of the conversation. So that being said, Jim, it's all yours.
Thanks, Lee. What we're looking at here is a block diagram of the StackMax system that Lee showed you a couple of minutes ago. And what the test that we're going to be running is going to be using stay PALs in box C. So we have a Linux-based stay PAL there we're using as a sniffer, and a Windows-based station will be our TWT client. And we'll be running traffic from an Ethernet interface in box A through the AP located there. The first thing that we want to check is to find out about devices that support TWT. So if we can just get a capture of a association request response capture of that, we can examine the beacons, the probe request response, the association request responses. And we want to check the HE-MAC capabilities information field. That's where we're going to see about TWT requester or responder support. So the picture we have here is from an AP that's advertising that it's a responder. In our demo here, we've got the ability of, these are the different types of requests and responses that can be sent. So the station can send a request where it just asks the AP for a set of parameters to set up a session. It can send a suggest message where it puts its parameters in and sends them to the AP to be approved. It can also send a demand message where the parameters it's sending are the only parameters it's going to accept, and it's not going to open up a session unless the the AP accepts them. So the AP side can send a response of an accept if it agrees with the parameters that were sent, and that would open up a session. If it wants to change them, it can use an alternate message to send back a modified set of parameters. In that case, the client will need to take a look at those parameters and either suggest a different set or send those back as a request, and then they would agree on them. The AP also has the option to dictate parameters, which the station must agree to if they're going to set up a session. And if the negotiations get to a point where they're not agreeing, then the AP is going to issue a reject, and that's going to end the session. There's also a TWT information packet that can be sent, and this could adjust the timing that we were discussing a little bit before. So it could send a new offset for the next TWT service period. And then there's a teardown message that can be issued by the requester if it wants to end the session. This can be sent at any time. It doesn't require response, and if it's got a certain group of parameters that it doesn't want to use anymore, it could send the teardown and then just start the process over and try to get a new session set up with different parameters. And in our demo, we're going to be able to generate the 3 different request messages that are circled there. The AP we're using is very agreeable, so we're just going to see accepts from that. And then we're going to run 3 different sessions, so we'll issue a teardown in between each one to close them down and then lead into the next one. So this is just a summary of the procedure that we'll be doing. So we're going to set up an octoBox test, start some throughput running. Then we're going to start a Wireshark capture in the background. From our Windows Stay Pal, we're going to generate TWT requests. So we'll do one of each of the 3. So we'll send a request, wait a few seconds to see how it affects traffic, then send a teardown, then move on to a suggest, and pretty much similar, repeat the process with a demand. We'll stop the trace at the end. We'll take a look at the TWT management packets, and we can look at some of the parameters that are inside those. And then we can use the Wireshark IO graph to take a little look further into what the packets look like and how the patterns show up there. Some of the key parameters that we'll be looking at is the first one is the target wake time, where that's where they're going to synchronize their clocks at the beginning of the session, and then there's going to be the time that's in there as an offset from the beacon timestamp of when the first service period is going to start. As far as determining the service period timing, the interval mantissa and the interval exponent are used to determine the length of the service period. So the formula to calculate that is they take the interval mantissa value times 2 times the interval exponent to get the length of the full service period. There's a minimum wake duration field, and the value there is multiplied by 256 microseconds. That will give the wake interval of it within the service period, and then just kind of end up with the remainder of the service period as the sleep time. So I've set up an octoBox throughput test here. So we can just go through a few of the pieces. I have a Linux Stay Pal here, can set up as a sniffer probe to do the capture for us. I've redirected the Wireshark output to a host, which is my local PC. I've got a Windows Stay Pal set up as and associated as a client, and an Ethernet endpoint on the other side of the AP that's going to generate the traffic, downstream traffic. So we start the traffic running. And when this is running, I've got a little batch file on the bottom that's going to generate the TWT requests on the Windows Stay Pal. So the traffic is already at the point where the first request was sent. You can see the effect it had on the traffic. Now a second request was sent. And these have different parameters for the exponents and the mantissas to set up different degrees of sleep and wake times. So those were the 3 setups. You grab the Wireshark trace and got a filter pre-configured that will sort the trace down and just give us the management packets to look at first. It's 900,000 packets, so there's a little bit of a delay while we wait for them to come up.
It came in under 1 million, though. That's
yeah,
that's new.
New record. Okay, so we can see now that the first packet is the setup issued from the client. Let me expand these a little bit and we can see some of the parameters that were in there. So we can see that this one came out as a request. Some of the parameters we were talking about is the wake interval exponent was 10, the mantissa was 512, and the wake duration was 255. We'll dig in a little deeper and we'll see how those affect the traffic pattern. The second packet was the response back from the AP, which was an accept, and it pretty much is showing that it agreed. It's got the same parameters here. And then this is the beacon offset, the timestamp from the offset from the beacon of when they're going to start this session. We waited about 4 seconds and then sent the teardown to end this session. We let traffic run a little bit further, and then we sent another request to suggest. This one has some different parameters in it where the exponent's 0 and the mantissa is 32,768 and wake duration 64. So in a minute, we'll get a look at what those actually do. Looks like the first one was and then there's the accept from the AP, followed by a teardown. And then we sent a demand request that was also accepted, and then another teardown. So,
hey, Jim.
Yeah.
There's one question. I don't know. You probably don't want to talk about it in great detail, but just maybe roughly. The question was, so how do you configure it to send these 3 different requests?
We have a program that can see a little bit of it here. This is from the Windows StayPal. So we have a utility here that pretty much covers the parameters that we're seeing in these packets. And you can see here, like the interval exponent, we set it to 1. The mantissa was 51,200. So this is being generated on the StayPal. So we can actually construct the packet and issue it and send it ourselves here. So we're going to use the IO graph to dig in a little deeper here. So it'll take a little bit of time to come up too, but you can also take a look here. So in test 1, the interval exponent was 10, the mantissa was 512, and the wake duration was 255. If we run that through the formula we had seen before, that ends up creating a service period of 524 milliseconds and a wake time of 65 milliseconds. Let me just zoom this in a little further. And then the second one, the service period was 32 milliseconds and the wake duration was 16 milliseconds, so kind of like a 2 to 1. And then in the third one, it was 102 millisecond service period with a 10-second wake duration, the 10 millisecond wake duration. So once this comes up, we can kind of take a look at these and get this out of the way so that we can see how it lines up with the throughput, effect on the throughput. Just zoom in just a bit. So we can see that the first issued commands brought this throughput down to under 100 megabits per second. And this is the one that had pretty long sleep times and the wake duration. So it was about 524 millisecond sleep duration with a 65 millisecond transmit time, but wake duration, which is about a 10 to 1 ratio roughly. The one in the middle was about 2 to 1, so we can see it affected traffic much less. And then the third one, which had a similar effect on the traffic, was much shorter times. It was about 100 milliseconds to 10, but it's still a similar 10 to 1 ratio. It's just that it's sleeping and waking much more rapidly than the first one, but still has a similar effect on throughput, basically because it's pretty much a 10 to 1 sleep versus awake pattern there. Multiple client tests, so I'll give it back to Lee and you can bring the presentation back up. So in this one, we have now 2 stations set up with similar parameters. Actually, they're exactly the same, except for the start times, which was issued by the AP. So we've got about a 4-second service period with a 65 millisecond wake period. And as you can see, there's the stations are separated by one is red and one is green in the IO graph chart here. So although they have the exact same parameters, by the offset in the timing of when they start, it keeps them from transmitting over each other. So that, and you can see that the timing is very precise and they're very periodic here. Second setup here, where the station 1 has the same parameters as before, where it's got the 4-second service period and the 65 millisecond wake period. But on station 2, we cut the mantissa down to 512, which cut its service period in half. So every 2 seconds, it's going to wake up to transmit. So you can see that the offset still keeps them apart, and that we'll see 2 wake periods for station 2 to 1 for every one of station 1. And their timing just keeps them separate so they don't transmit over each other at any time.
All right. Thanks, Jim. We're going to wrap up now, but before we do, are there any other questions for Jim on what you've just seen? I think it's probably the first time many of you have actually been able to see TWT work. It was quite a bit of wrestling to get this all pulled together as a test like this in the test bed. So, you know, if you have questions, let us know. We'll be happy to talk about them. So I see something coming up here in the chat. TWT is more efficient in 6G than in 5G. I guess, so you're talking about 6 gigahertz and 5 gigahertz, and it's a question. Since the AP services only 11 AX clients and does not have to worry about legacy power save. Yeah, I think that's probably true in some sense, right? I mean, if everyone is supporting TWT and you don't have devices that are essentially kind of not able to be scheduled, then yes, I imagine the whole system would be somewhat more efficient. I don't know of, I imagine actually that there are people who have done maybe some calculations or, you know, papers on, you know, how much trouble you get into. We talked about this on a previous call, and somebody actually mentioned that it's possible, though, to use things like the nav to keep devices from transmitting. So, you know, a clever AP could keep legacy devices off the air while it serviced the, you know, the AX TWT capable devices. So I think there are ways to make it all work, but I agree, you know, typically when everybody is speaking the same language, it's going to be somewhat more efficient. Can you guys measure the effect on the battery life during this demo? That's a great question. We don't yet, but that idea has certainly come up, and it's something we have, you know, somewhere in our sites. You should probably maybe reach out. We can talk about this. I think we would be motivated to come up with a good test, especially with a customer who is particularly motivated to have that answer. But yeah, that's come up. We don't have that as part of the test, but it's definitely a common thing to do when you're doing power save, and it is something we think about. We've been thinking about. Is the traffic from the station during the awake time triggered by the AP, or does the station need to contend and go through a back-off procedure before transmitting? What was used in the demo? I don't know. Would you like to take that one, Jim?
Yeah. This was unannounced, so it is on a schedule. There is an announced mode. We haven't really found a lot of devices that are supporting that, but in an announced mode, they would have to send QS null or PS hold packets to show that they're ready for transmissions, even during the scheduled service periods. I'm not sure if that answers the question completely.
The next person wants to know if we can share the IOgraph setup information in the Excel worksheet for the wake time calculation. I think maybe just contact us directly, and we can have that conversation.
Yeah.
And then, does TWT feature mainly target IoT or general use to replace legacy power save mode? I don't think it's only focused at IoT. I used the IoT as kind of a good motivation for it, and, you know, some aspects of Wi-Fi 6 in general. But and again, I don't know how it will necessarily be used. Like, are people going to say, well, legacy power saving mode now is no longer necessary, we're just going to use TWT all the time? I don't know about that. But, you know, I guess I didn't mean to imply that IoT was the only application here, but I do think it is an important one, and it's one that kind of makes the value of TWT really sort of stand out, because it's the kind of application where you really do want to go from sleep times, or let's say battery life, where, you know, a day running on battery is fine, to where, you know, to a case where, you know, 6 months running on a battery is only kind of just good enough, right? And you expect more like a year. So it's a, you know, quite a big difference. And so I wanted to highlight it there. Whom should I contact? I think we can reach out. So Kristen, you're typing an answer. Okay, so you'll deal with that. I think we have some we have contact information at the end of the presentation, and we can also reach out directly to anybody who says something here that they'd like to talk to us about this. Okay, so I think we're coming right up on an hour. And so let me just quickly wrap up with our sort of final comment, which is just to summarize where we are. Speaking of the IoT, though, you know, speaking sort of based on this conversation about the IoT, I think what's important is a comment I made before, which is that, you know, Wi-Fi is already deployed in a lot of places where the IoT networks will be or already are. And so there's an extremely strong desire from everybody, device manufacturers, network operators, IT managers, for the existing networks to be able to, support devices well, without necessarily needing an overlay network of some sort. Legacy Wi-Fi definitely has some drawbacks for IoT use around bandwidth efficiency and power saving, but Wi-Fi 6 really has added some strong functionality to Wi-Fi, making it a real contender in the IoT space, using things like OFDMA and TWT for aggressive power saving. So that being said, I see another question which I will take a look at in a minute, but just want to remind everybody, again, this is number 12 in our series. The previous 11, this is a slide with some links to them, but they're all available on our website. You should easily be able to find them there. And this information will be posted in the next couple of days. And as far as contact, reaching out to us, you can always reach out there. I think there's 2 addresses here, sales and info. And somebody will pick up those messages, and we'll get right back to you. Thank you all for attending. As I said, we are really happy. We enjoy doing this, especially during this time when it's difficult to travel. We hope you're enjoying it as much as we are. If you have other topics you'd like us to cover, you can use these same addresses to send us those ideas as well, and we'll take a look at those. We look forward to seeing you next time. So thanks all for attending.